Okay, for what we have in this worksheet set, okay, again, we're looking at quadratic functions and looking at what we have in the first problem. Okay, we have a graph, okay, that is in the form of a parabola, and so this graph is referencing a quadratic function. And just looking at the image, okay, we have right away the answer to the first part of the question, and it's asking if the parabola opens up or down. Okay, in this case, you have both sides moving up. In this case, we have the graph to be moving upward. Now, in the case of the axis of symmetry, again, that's going to be the vertical line, okay, that divides the graph into two mirroring halves. Okay, and if you notice, okay, if I look at splitting this graph right down the middle, okay, and it looks like for this image anyway, see if I can get this lined up in satisfactory form. And if you notice, we have for the image, okay, it looks like it is going to pass through x equal to -2. Okay, so we have running through the x-axis. Okay, so we have x equal to -2, and that will be the equation for what we have for the axis of symmetry. And for what we have in the case of the intercepts, okay, for the x-intercepts and the y-intercepts, again, the x-intercept is going to be where the graph crosses or touches the x-axis, and the y-intercept will be where the graph touches or crosses the y-axis. Okay, and for what we have for the x-intercepts, looks like we have x equal to -1 as well as x equal to -3. So we have for the intercepts regarding the x-axis, okay, so it looks like we'll have x equal to -1 as well as x equal to -3 if we leave what we have in equation form. And for what we have with regard to the y-intercept, okay, we have, looks like that one's going to be on y is equal to 3, and so that would be the equation we have, okay, for the y-intercept. And again, for the coordinates, x equals -1, x equals -3, you would have location -1, 0 as well as -3, 0, and for y is equal to 3, as an ordered pair, we would have 0, 3. And for what we have with regard to the coordinates of the vertex, okay, and we have, in this case, we have the minimum. Okay, so it's like we have x at -2 and y at -1, and that is going to be the minimum. So for the vertex, we have it -2 and -1. Okay, for the second question, okay, it says to consider the following quadratic function. And now this function we have presented in standard form, and we're looking at translating, okay, the layout in terms of the vertex form, okay, and we're to give the vertex of the graph. And now for what we have in the case of part A, okay, so we've got for the standard form of this quadratic function, okay, so we have f of x is equal to 3x squared minus 30x plus 73. And looking at, again, initiating the process of transitioning from the standard form to the vertex form, we can proceed by separating the variable terms apart from the constant. So we have for the variable terms, again, we have 3x squared minus 30x, and upon separating, okay, now I want the first term in the parentheses to be just x squared. And if you notice, we have for the leading term, we have the coefficient 3. So what I'm going to do here is rewrite the equation with 3 factored out. So in this case, you have f of x is equal to 3. And 3 goes into the binomial 3x squared minus 30x x squared minus 10x times. And upon factoring out 3, okay, we're ready to cross over to the stage of the completion of the square. So I'm just going to duplicate this item. And looking at completing the square. So again, with the leading term of x squared within the parentheses, okay, the completion of the square, I can proceed this time around. Okay, so looking at what we now have next to x, we have the coefficient negative 10. And if I take half of this, I've got negative 10 divided by 2 is negative 5. And then squaring out negative 5, okay, this will become 25. And what I'm going to do here is that as I draw nearer to the vertex form, I'm going to take 25 and add to x squared minus 10x. Okay, so now we've got f of x is equal to 3 times the quantity of x squared minus 10x. Okay, we have followed by the addition of 25 I got plus 73. Now I want to have things balanced out where I could, in a sense, reverse engineer what I have here back to what we had with the original standard form. So by adding 25 to complete the square, what I'm actually doing in the overall picture is that as at the front, I'm adding not 25 but 3 times 25. So I'm creating a surplus of 75, and I'm going to balance this out by taking away the same amount. So looking at what we have in the rewrite, so we have f of x, we have is equal to 3 times the square trinomial x squared minus 10x plus 25, and we have 73 minus 75. Okay, so that will go to negative 2. Okay, and again, just checking, we have 3 over the trinomial. We've got 3x squared minus 30x. 3 times 25 is 75, and 75 minus 2 returns to 73. Okay, and crossing over to what we have for the vertex form. So we got 3. That is going to be the value of what we have for a. And then we have for the x minus h to the second part. Again, we have with x squared, okay, we have that to be the square of x, and the constant that will be used to fill in for the minus h portion. Okay, notice in initiating the completion of the square process, okay, after taking half of negative 10, okay, I squared out negative 5, and whatever I square in the completion of the square stage, that is going to return as the representation of the h portion in the vertex form. So the vertex form is going to be 3 times the quantity of x minus 5 raised to the second minus 2. Okay, and for what we have in terms of identifying, okay, the vertex. Okay, right now we got for the coefficient a, okay, that is 3. 3 is positive. And so you would have from this, okay, you would have that the graph is going to open up. And for what I have in the case of the h value, again, the h value is going to be the 0 of x minus 5, so we have that h is equal to 5. And for the k value, we had the subtraction of 2 at the end, so we had that k is equal to -2. Okay, so we got for these items, okay, with h at 5 and k at -2, again, we're going to have the axis of symmetry, where we will have x equal to 5, and for the vertex, we're going to have the ordered pair hk, whereupon we have at 5, -2. Okay, and that will be the outcome that we have as we translate out to what we have in the case of the vertex form and the resulting vertex. Okay, so just looking at what we now have, at least in the context of graphing, okay, and just key items here. Now we can identify some of the items that we have, namely the intercepts. Okay, so if I'm looking at arriving at, let's say, the graphing, okay, and what I can do here is that for just items here, okay, so we got, I can just select values of x around the constant 5, okay, and we have for the y value, we have y is equal to 3x squared minus 30x plus 73 and we start to pair up. Okay, so if you notice in the middle, okay, we have, you can either use the vertex form or the original standard form. Now, you're going to have for x, again, we have at 5. Now the y value, okay, now again, this will work for both the vertex form and the standard form, and I'm just going to take this as a sample. Okay, so you have 3 times 5 squared minus 30 times 5 plus 73, and I'm going to sort of cluster all this together. 5 squared is 25 times 3 is going to be 75, and we have minus 30 times 5, so we have minus 150 plus 73, and that's going to return to -2. So we have for the pairing of x and y, whenever x is set to 5, again, we had the return to the vertex and values that you can plug in, okay, say in proximity to x is equal to 5. Okay, so we could select like a couple of values of x, okay, 1 less than, 1 greater than, and 2 less than, 2 greater than. And if I run through the treatments, okay, so if x is 4, so I have 3 times 4 squared minus 30 times 4 plus 73. Okay, so got 4 squared is 16 times 3 is 48. We got minus 120 plus 73. And for what we will have in the process, okay, will come out to positive 1. And guess what? Okay, now both sides will mirror each other about the axis of symmetry, which we'll get to. Okay, and for what we have in the case of x equal to 4 and y is equal to 1, and guess what? For one space over, you're going to end up with the same y value, and that is going to be equal to 1. Now, if I plug in 3, which will be 2 spaces to the left, and 7, which would be 2 spaces to the right of the axis of symmetry, I'm going to come out to the same y value. Okay, and we'll just take for 3 times 3 squared, so that'll be 27 and we have negative 90, and we have plus 73. Okay, so 27 minus 90, that would be a negative 63, then followed by the addition of 73, so it would come out to 10. And for 7, you're also going to come out to 10 itself. So ordered pairs we're going to have in the mix, so we have 4, 1, 6, 1, 3, 10, and 7, 10. So if I graph the function itself, okay, so we got in the mix, okay, so we have 5, negative 2, and again we have like 6, 1, 4, 1, and then we have 7, 10, as well as 3, 10. And again, not the graph itself, but you do have your axis of symmetry that will cut through the vertex. Okay. And now for these points that I have plotted, okay, you have for the graph of the parabola, again, it's going to open up and will pass through these points. I'm not perfectly drawing according to scale, but this will be the essential dynamic of what we have with what we have for the graph of the quadratic function. And again, so this will be the outcome for what we have in number 2. Okay, now for what we have in the case of the determining the range and the domain. Now the range, you're looking at the y values, and for the domain you're looking at the set of x values. Okay, all covered by what we have in the graph of this particular quadratic function. Now if you notice, we have a quadratic function. Now we got the vertex. Looks like that is going to be located at negative 4 and negative 2. Okay. Now if we look at the domain first, okay, notice you have continuous motion horizontally. Now you have the function is opening upward, okay, and we have moving to the left and as well as moving to the right continuously. Now it's a very gradual process, but you're looking at the extremes. You're looking at moving to the left gradually toward negative infinity, and for what we have to the right, we have moving gradually out to positive infinity. And everything between negative and positive infinity we're going to have covered by the quadratic function. So for the domain, you're looking at the set of x values, and the domain for the interval notation, we have the set of all real numbers. Now for what we have in the case of the range itself, now the range is not going to be the set of all real numbers, because you're looking at starting from the minimum y value, and the minimum y value, okay, is going to be what we have for what we have in the vertex, okay, and so we have the minimum y value situated at negative 2, and then we have from negative 2, notice as the graph opens up, okay, the y value increases from negative 1 to 0, 1, 2, and you have continuously increasing throughout. We have y to be approaching positive infinity. Okay, so we have from the minimum. Okay, we have from and including y is equal to negative 2, and since negative 2 is included, this will be in the bracket. And again, we have for the rest of the range, we have y to be trending to a continuous increase toward infinity, and that will be the result of what we have for both the range and the domain. Okay, now for number 4, okay, we have a medical equipment industry manufacturing x-ray machines, and we have the unit cost in dollars to make each x-ray machine. That's going to depend on the number of machines made. And if X machines are made, then the unit cost is given by the function where we have C of X is equal to X squared minus 400X plus 45,116. And it's asking how many machines must be made to minimize the unit cost. Okay, now we have with this equation. Okay. All right, so we have C of X is equal to X squared minus 400X plus 45,116. Okay. Now, I can get to the vertex form from the standard form, but I'm going to go a different route in this particular case. And in fact, okay, I'm going to stick with the standard and show you the pathway to getting to the vertex through the use of the coefficients of the standard form. Okay, now we have x squared, which we have implicitly to be 1x squared. And reminiscent of we were looking at the quadratic formula and the quadratic equations. Okay, we have like a was equal to 1, okay, and then we have for the x term coefficient we have b, and in this case we have negative 400, and for any constant that follows, okay, that is a reference to c. So you have 45,116. Now, in looking for the minimum cost, okay, first of all, okay, the cost is contingent upon the number of machines made. So to lower the cost, we're also looking at minimizing the number of machines. So for the minimum number of machines, now we got using the coefficients at hand. So we're looking at x is equal to what will be the ratio. Instead of h, like in the vertex form, we're going to go with negative b over 2a. And if we substitute, we're looking at the negative of negative 400 all over 2 times 8, which in this case we have it 2 times 1. And so we got positive 400 divided by 2. And so we have, in this case, we have at 200. And so in terms of how many machines must be made to minimize what we have for the unit cost, okay, you have 200. And I'm going to throw this in. Okay, now if I'm looking at the minimum cost, now the minimum cost, okay, you're going to have at x is equal to 200, again, being the number of machines. So referencing what we have with this formula. Okay, so if x is equal to 200 and I want to minimize the cost, so I'm just going to say have C of 200. So you have 200 squared minus 400 times 200. And we have plus 45,116. Okay, and for the numbers here, so you got 40,000 and 400 times 200. Okay, you had the subtraction of 80,000. And adding back in 45,116, it turns out that we have for the minimum cost, okay, this would be at $5,116. Okay, now for number 5, like the cost problem in number 4, I'm going to use this standard form as opposed to the vertex form. And now for what we have in the case of what we have with the variable h. Okay, and now we have a ball that is thrown vertically upward, and after t number of seconds, its height in feet is given by the function, whereupon we have h of t is equal to 104t minus 16t squared. And we're looking at the maximum height that the ball will reach. Okay, so looking at what we have for this equation now, if I'm to translate what we have to either standard or vertex form, okay, what I need to do is to have the terms in descending degree order. Okay, so we have rearranging the terms. So if I put the square term at the front, I have negative 16t squared plus 104t. All right. Now, again, if the leading coefficient is negative, then the vertex is going to be the maximum. If you were to graph, you would have downward motion from the vertex, where the vertex would be the peak point. And now for t, you're looking at, again, the amount of time. And for what we have, at least setting the stage, if I use the standard form to get to, in this case, the maximum. Okay, so from this quadratic function, okay, so you have a is equal to negative 16. We have a first order term with a coefficient 104. So you have b is equal to 104. And since I don't have anything to follow this, okay, you would just have like your c value would be negligible. And looking at the time at the maximum height, okay, so we're solving for t as opposed to x, okay, but you're still going on the same precepts, okay, because you treat t like you do x in the formula. We have is equal to negative b over 2 times a. And for negative b, we have the negative of 104 and 2 times a. So you have 2 times negative 16. And for what we have in the ratio, we have negative 104 divided by negative 32, and simplifying, and I'm going to put this down as a decimal, so we're going to have it 3.25. And now, for what we have in terms of the maximum height, okay, this will be attained whenever the time is at 3 1/4 seconds. Okay, so we have for the maximum height, again, this is achieved, okay, whenever the time is at 3 1/4 seconds. Okay, so for what we're going to have here, you can either use the standard form conversion or the original we had laid out. So I'm going to do here, I'm just going to say, plugging in 3 1/4 for t, so we have h of 3.25. And we have is equal to 104 times 3.25. And we have minus 16 times the square of 3.25. And for what we're going to have in this particular case. Okay, so we have with the numbers. Okay, we have 104 times 3.25. Okay, so that part will be 338. And for the square of 3.25, okay, so we have minus 16 times 10.5625. And multiplying that number by 16, okay, so you have minus 169, and guess what, 338 minus 169, okay, that is going to be 169, okay, and so we have for the final answer, okay, we have 169 feet. Okay, now for question number 6, it says to find the range of the quadratic function. Now what I have decided to do is just go ahead and insert, okay, the image of the quadratic function itself, and I'm going to throw in the domain as well. Okay, now for the domain, okay, you're looking at, okay, the x values. Now we've got the graph of the quadratic function where the vertex is going to be the high point in this case, right? So the graph opens down and you have moving continuously downward as well as to the left and to the right. Now for the domain, okay, you're looking at gradually moving continuously to the left, also continuously to the right as the graph falls from the starting point, namely the vertex. So for the domain, you have continuously to the left as well as moving continuously to the right. So in this case, the domain, we have the set of all real numbers. Now, for what we have in the case of the range itself, now you're looking at the y values. And for what we're going to have for the range, okay, and now, again, you have the graph, okay, to peak at the vertex. The vertex is going to be the high point, so you're looking at maximizing at the y value of 1, and then everything else is going to be less than. So in this case, the value of y falls, okay, as we proceed to go out, and so you have continuous downward motion where we have y to be approaching negative infinity. So from the minimum to the maximum, okay, we have for the range, okay, we had the minimum y value, okay, begins from negative infinity, and we have approaching and including the y value at the vertex, which we have with 1, and again we have the 1 to be closed, okay, since the quadratic function is inclusive of the vertex. Okay, for number 7, okay, I had decided to insert the graph of this particular quadratic function as well, and it's asking for the range and history repeating itself. Okay, I'm going to include the domain. So we have for the graph of the quadratic, you have opening up this time around, and the motion, we have continuously moving upward and also to the left and to the right, and you have all the x values will be covered, okay, where we have the domain, again, is going to consist of all real numbers. So the domain, again, we have between negative and positive infinity. And for what we have in the case of the range itself, okay, now in this particular function, okay, now we have the vertex to be the minimum, okay, and the range is in reference to the y values. So the vertex contains the minimum y value, which in this case is the k value at -4, and then from -4 the y value continues to go up, and you have in the process as the graph moves up, you have the y value to be approaching infinity. So for the range, we're going from and including -4 from the vertex point, and the rest of the y values will be higher than -4, and we have continuous increase out toward infinity. So for the range, we have between -4, inclusive, and infinity. All right, for number 8, it says to find the equation of the quadratic function f whose graph is shown below. Okay, and if you notice, okay, we have with the graph, okay, we have our vertex point to be the maximum, where we have at 5,2. Okay, so just laying the foundation. Okay, so we got a vertex and doing a bit of a return to the vertex form. So we got the vertex HK is equal to 5,2. Okay, so again, we have that h is equal to 5, and k is equal to 2. And for the vertex form, okay, so again we have for y, so we have y is equal to f of x is equal to a times the quantity of x minus 5 squared so we have with the vertex form, okay, so we have y is equal to f of x, which is a times all of x minus h squared plus k, and if I plug in 5 for h and 2 for k, so you have at the moment, okay, so you have y is equal to f of x, and we have is equal to a times the square of x minus 5, followed by the addition of k. All right, and to get to what will represent a, we can use the other point that we have specified, and that's going to be the x-intercept 6, 0. So we have, using what we have thus far, so we have that x is equal to 6 whenever y is equal to 0. And if we go back to what we have for our previous equation, okay, so you got y is equal to a times the square of x minus 5 and plus k, which we're going to have at plus 2. And if I substitute, okay, 6 for x, 0 for y, so we're going to have in the rewrite, so we have that 0 is equal to a times the quantity. Now we got 6 minus 5 squared and we have plus 2, and so we've got 0, 6 minus 5 is 1, and 1 squared is 1, so we're looking at 0 is equal to a times 1 plus 2, or a plus 2, and from this we're going to have that a is equal to negative 2. Okay. So as we put back, okay, and transitioning, okay, so we had the y was equal to f of x is equal to a times the square of x minus 5, followed by the addition of 2. And with a now determined, we can say that y is equal to negative 2 times the square of the binomial x minus 5, followed by the addition of 2, and that will be the equation of that particular quadratic function. Now for what we have in number 9, okay, the nature of the problem, similar to number 8. Now we got another quadratic function where the graph is opening downward. Okay, so we got the vertex situated at negative 1, 7. Okay, so we have that h is equal to negative 1 and k is equal to 7. And setting the stage for what we now have. So we have y is equal to f of x is equal to a times the square of x minus h, followed by the addition of k, and then again substituting negative 1 for h and 7 for k. So at the moment we have y is equal to f of x, and we have a times, okay, and we have x minus negative 1, so this will translate to x plus 1 raised to the second, and have followed by the addition of 7. And in the determination of a, I can utilize negative 2, 4, okay, so if I substitute 4 for y, and negative 2 for x from the previous step. Okay, so having the rewrite. So we have that 4 is equal to a times all of negative 2 plus 1 quantity squared. Then we have followed by the addition of 7. Okay, so we got 4 is equal to a. Negative 2 plus 1 is negative 1. And the square of negative 1 is going to be a positive 1. And so we have 4 is equal to a plus 7. And this time around, we're going to have that the value of a will be negative 3. And so for the vertex form of the equation of this particular quadratic function, we will have that y is equal to f of x is equal to negative 3 times all of x plus 1 raised to the second, followed by the addition of 7. And that will be the final answer.